Recording in progress.
Sweet. Awesome. Good. Okay, let's take a look at the bottom of the green. So 1 squared plus 2 squared plus 3 squared and so forth, right? That would just keep going forever, right? That would not converge because like could I find the sum of all those terms and be for sure knowing what it is? No, right? That just goes on forever. And let's also look what's in the red box here. Convergence divergence of an infinite series. So we add the terms of finite series, you'll get a finite number. We talked about that. Like when we talked about like all the seats in Harmon Auditorium, we started with 16 seats. Every row, I assumed, increased by 2 seats. It doesn't all, I don't think it actually happens that way, but we assumed that. And ultimately, we found that it's to converge to 700 seats, right? Because I told you there's a finite number of rows. There's not infinite rows in Harmon Auditorium, right? It actually has to end somewhere. So of course, if we have a finite series, it ends. But we have an infinite series. Sometimes we can find a sum, sometimes we can't. And so there's 3 different scenarios to consider. It can approach a finite value for an infinite series, so we say it converges. It just keeps getting bigger and bigger, so it diverges. Or it can oscillate between 2 different numbers, and that also would diverge. Do you guys remember what type of series would converge? What type of infinite series would converge? Geometric series when R is what? What was between what? Perfect, non-inclusive, right? So if you have this here, so that's the one test I'll show you guys today, which we've kind of seen already, where to verify if a series will converge, if it's geometric in nature, and if R is between -1 and 1, great, it converges. If it's not, it won't. What about an arithmetic series? Can arithmetic series ever converge? No. You just keep adding the same thing over and over again.
If E is 0,
if E is 0, you're saying
0, then
yeah. I mean, like for example, what if I have like 4 plus 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 4? So that is technically arithmetic because you're adding. What's the common difference here? 0. But if I do this infinite number of times, will this sum ever converge? No. It just goes on forever. It keeps getting bigger, right? You can also think of like a geometric where you multiply by what? But remember, it has to be non-inclusive for -1 and 1 for it to converge. So arithmetic series won't converge. Typically, they'll just keep going up towards positive or down towards infinity. And partial sums, we're going to talk about that on the next page. So let's keep moving here. All right, so now we have the summary done. Let's now move on to the examples. All right, so for each infinite series, and it's infinite because you have the top number. And by the way, this is just the way Ms. York put this in her, this way she formatted, but it's the same thing as saying this. Just so you know, it's the same thing. So the lower number is where you start, the higher number is where you end, but we're not ending, right? Hence it's infinite. And what's my formula? My formula is n, right? So first thing we'll want to do is let's just figure out what this really is. What's really happening here? What does all this mean? Actually, I'll just do it right here. What does all that mean? What's your first one is 1, then 2, then 3, then 4, and then ... Okay. So for the first part, it's saying to find the first 4 partial sums and write the partial sum as a sequence. Okay. So when you do the partial sums, you guys remember this, right? S sub n. So what we're going to do is we're going to do S1, S2, S3, and S4. So S1 represents the first partial sum. Okay, so that's going to be the first partial sum. Well, obviously, if I just sum up one term, what do I get? 1. Okay, now, what would the second partial sum be? It'd be 3, right? Because you're doing 1 plus 2. which is 3. And the reason why we're doing this is that we want to apply a calculus principle to this. Limits, right? We're taking limits and approaches infinity. So that's what we're going to try to accomplish here. Okay, well, how about the third partial sum? 6, good. How about the fourth one? 10, and so forth. Okay. So if I write as a sequence, it'd be 1, 3, 6, and 10. Now, this is its own pattern, right? Pattern recognition. It's its own pattern. What pattern are you noticing among these 4 numbers? It's not a common difference, obviously. But if you look at the pattern among these 4 numbers, like what are we doing to get from the first one to the second one? We're adding. Then what are we doing from the second to the third? Adding 4, adding 5, and so forth, right? So what we're going to try to do is we're going to try to generate a formula for that. Okay. So that's the first part, right? So we found the first 4 partial sums, rows of sequence. Cool. Now the second bullet point, determine if possible the S sub n formula, which really is just the explicit formula for finding the sum of an arithmetic series, right? If you think about it. So how would I express this? So what we want to do for the second bullet point, let me erase because I need some more space here. So now for the second bullet point, our task is the following. Express the sequence express the sequence 1, 3, 6, 10, ... as a formula in terms of n. Well, if you think about it, every term is a sum, right? So how did we like what would the first term be here? 1, right? And when we did an arithmetic series, you always added 1 to the last term, right? The last term is just going to be n times n over 2. So if you think about it, like 10, for example, that should happen when n equals 4. If I put a 4 to this, what's going to happen? 1 plus 4, which is 5. 5 times 4, which is 20. What's 20 divided by 2? 10, good. So so this is, it's kind of mind bending a little bit, but every term in 1, 3, 6, 10, ... every term there is actually representing the sum of the series of n terms. So every number, 1, 3, 6, 10, 16, 26, and so forth, right? Every term is represented by this formula. And what is this formula to begin with? Wasn't that the arithmetic series formula, right? So whatever n is, what you got to do is you got to take the sum of the first term plus the last term, which is 1 plus n, and multiply by the number of pairs. And how do we get the number of pairs? N over 2. So that's how you can express each sequence using that formula. So now what we want to do for the third bullet point, I'll switch colors for a bit of contrast. Determine if that series converges diverges by examining the n behavior of S sub n. Okay, so I'm going to take the limit as n approaches infinity of that expression. Again, this is not an expression that fell out of the sky. We've seen this already. That's just the sum formula for a arithmetic series. And again, when we're looking at partial sums, every term represents the sum of n terms of an arithmetic series. If you think about it, I can clean this up, right? Wouldn't that just be n squared plus n over 2, right? So n squared plus n over 2. So we can think of it as a rational expression, right? Now, what I could do next is multiply top and bottom by 1 over n squared. Correct, but I'm just showing the formal way of proving it. That's all. We're cool so far with all that. Okay, so this is taking a calculus perspective with these series, right? Taking the limit as n approaches infinity, and what does that reduce to? 1 plus 1 over n squared.
Sorry, 1 + 1 over n.
1 over n. You're right. Sorry, and 2 over n squared. So wouldn't that just be 1 plus 0 over 0? What would you what would we deduce about that? What would that become? What was that? Sorry? Is this gonna be infinity? Yeah. Because what you're doing is that goes away, the 1 over n. So now you're doing 1 over a tiny number. What's 1 over a tiny number? A big number, exactly, right. Like that's like 0.001, right? So you're doing 1 over that. So essentially this will diverge. So this series, it's a series because you're adding a bunch of terms. And what do the terms represent? They represent
I thought it was a sequence.
it's a sequence initially, 1, 2, 3, 4, but the sum itself is going to be what we call the partial sum. Like for example, n is 4, that's the fourth partial sum of this vertex sequence, right? When n is 5, that's the fifth partial sum and so forth. So essentially, if you want to determine if the series itself diverges or converges, you have to be able to ask yourself, well, what formula can I use to express the sum of any term? See, for example, if the top is 4, right? If the top is 4, then of course it's 10. If the top is 5, it's going to be 16 and so forth, because you're adding up all those terms. And what does that pattern do? If I take the limit as n approaches infinity of that pattern, we see it just goes towards infinity. So that's really what we're trying to look at. We're trying to see it through the lens of a series, not so much a sequence anymore. As a sum. So we essentially we're writing a new pattern. 1, 3, 6, 10, 16. We're not looking at 1, 2, 3, 4. Of course, that sequence diverges. Of course it does. Because the infinite term is, I don't know, right? It just goes forever. What we're more concerned about is the sum. Like let's do a geometric one. I think when we do a geometric one, this will start clicking. Okay, so let's look at this one next. All right, so for part B, let's just write the terms. What's going on here? Where are all the terms here? If I plug in 0, what do I get? 1. If I plug in 1, and by the way, why am I plugging in 0? Yeah, so you have to be mindful of the index, right, of where you're starting. And then what's the next one? Sorry. 1/3, 1/9, 1/27th, and it goes on forever, right? Now, here's the key difference. Sequence versus series. Here's the key difference. The infinite term converges to what? If I kept going forever and ever and ever, let's say I asked you for the 1,000th term. The 1,000th term is close to what number? 0. Good. So the infinite term converges to 0. Okay. Now here, the infinite sum converges to what? Sure. Not 1. Yeah. Remember the formula for that? Converges to this. A1 over 1 minus R. A1 is 1. What's your R? 1 over 2/3, which of course is 3/2. So that hopefully might clear up what was going on part A. Part A, we were not evaluating we're not taking a limit as n approaches infinity of the sequence. We took a limit as n approaches infinity of the sum,
The partial
the
sum.
partial sum, exactly. We do the same exact thing here. So what I expect to happen is when I take this limit, see, here's the difference. If I take a limit 1/3 to the n, forget about the sigma. Imagine sigma didn't even exist. Just focus on 1/3 to the n. If I took the limit of 1/3 to the n as n approaches infinity, what do I get? 1/3 to a large number. What's that gonna be?
Zero.
Zero. Now, with the sigma back in play, if I take a limit of all this, what's that gonna be? 3/2. That's the difference. Granted, for part A, the limit of the sequence and the series are both infinity, because if I do 1, 2, 3, 4, the infinite term, of course, is infinity. And if I look at the limit of the partial sums, 1, 3, 6, 10, and so forth, that was still infinity. But when I'm taking a limit of a series, I have to be mindful of the formula that I'm working with, right? So in this case, I'm taking the limit of a series, not a sequence for part B, and even part A as well. So what I need to do, so I'm going to clear this right now. So I already did the first bullet point, right? I've listed the first four terms. But let's get the partial sums now. What are the partial sums going to be for this? Actually, let me erase this other junk here. Okay, so actually I'm still working on the first bullet point. We're not quite done yet. So the first bullet point, the first four partial sums. First four partial sums. So S1, S2, S3, and S4. So this is going to give me its own sequence afterwards. What's my first partial sum for this pattern? 1. What's my second partial sum for this pattern? Good. And I'll just tell you the other ones. Dude, you guys are awesome. You said you guys didn't know fractions. You guys didn't know your fractions really well. 4/27. Awesome. Very good. Good, good. Do I see this eventually converging somewhere? Yeah, I kind of do a little bit, right? Because we got 3 halves of 1.5. What's half of 9? So yeah, kind of looks at the end there, like what's half of 27? 13.5. So yeah, that looks like it's getting pretty close to 1.5, right? So what we're gonna do, and now remember the formula for Sn. What's the formula for a sum of a geometric series? A1, 1 minus r raised to the n power, or 1 minus r. So I'm going to take, so now I'm ready to move on to part B, or the second bullet point. I'm going to take the limits n approaches infinity of that. What's my A1?
1.
Good. Right. It is 1 because remember we're raising to 0 power. What's my r value? 1/3 raised to the n over 1 minus. Geez, can't do 3s here. Okay. So we're cool so far? All right. So now, if I take my limit, as n approaches, let's clean this up a tad, right? If I clean it up, I should get, what does this become again? And do I have to flip it? Yep. So hopefully you guys can see that, how I got 3 halves. I flipped to 2/3. We're good, cool with that, all right? And then I give 1 minus 1/3 raised to the n power. Okay. I can distribute, and I'll put another big bracket because I feel like it. So what we're doing is we're taking a calculus perspective with these series, right? By doing the limits as n approaches infinity. If I distribute, what do I get if I distribute? 3 halves minus. Okay, cool. If I now evaluate this limit, what's 1/3 raised to infinite power? No, 1/3 raised to infinite power.
0.
If I raise 1/3 raised to if I raise a fraction to infinite power,
Oh,
what does that power become? 0, right? No, the exponent becomes. I'm not sure if that's your answer, Thomas. The exponent becomes infinity, but 1/3 raises to infinite power. That whole embodiment becomes 0. So you have 3 halves minus 3/2 times 0, right? So all this right here, that makes sense, right? And so we wind up getting this 3/2. So now I found that limit of that partial sum, right? So the formula I got, right? The formula is easy. Well, I mean, I kind of wrote it over here. That's my formula. And I took the limit. So in this case, we say it converges. Because it settles on a final number. Okay, so that's a test of convergence. This is a test of convergence using a geometric series. That's one of them. There's 9 more that if you take AP Calculus BC, you'll learn with Ms. York. So I'm not going to go over those other 9 because we just don't do that in this class. So does that make sense what we're doing here? Okay, so let's keep moving. All right. So let's look at this one now. Now, this is an example of an oscillating because you see it's going to go back and forth between 2 different numbers, right? So same thing again. Let's write out the first 4. Well, let's write the pattern first. What's the pattern again? If you raise this into 1 power, what do you get? +1, plus -1, +1, plus ... right? So if I write my partial sums, what's my first partial sum? What's my second partial sum? What's my third partial sum? What's my fourth partial sum? And it's never ending, right? It just keeps doing this the song and dance. -1, 0, -1, 0, -1, 0, and so forth, right? So what you could say here is you could just make a statement. If possible, I mean, you can't really write a formula so much for this. I mean, it's kind of weird. I mean, the formula itself, yeah, I mean, it's it's not really anything we really could say, but if you think about it, because this oscillates, because the partial sums oscillate, which means goes back and forth. That's what oscillate means. I can't spell. That is terrible. Here we go. Oscillate between -1 and 0. The series of this guy, we say diverges.
Didn't diverge to negative infinity?
No, because you have a bunch of canceling, right? Because it just keeps going back and forth the sums.
Yeah, but
Every even partial sum is 0. Every odd partial sum is -1.
right, so that won't.
But the thing is that like we can never settle. No, we can never settle on a certain number, right? So it just oscillates between -1 and 0. So that's what's happening for that one. So you can just make that statement. That statement's good enough. I mean, if you want, you could try taking a limit. You could try taking a limit of this, but that doesn't really do us any good. Sometimes we just use more of an intuitive approach. Like, okay, here's what I see is happening, and it's going back and forth. So sometimes we could draw that conclusion. If it's oscillating, you just make that statement. It diverges. So, bless you. Okay, we're good on part C. Okay, part D. Ooh, that's an interesting one. Okay. So this is what we're going to call, and you'll see why in just a moment. This is a really fun one. This is called a telescoping. It's called a telescoping series. Okay, initially it looks kind of weird. 3/n² plus 7n plus 2, right? Now, what did we just do? This is called fraction decomposition. You will use this technique often in BC Calculus for other types of things that you'll do in that class. So why is it called fraction decomposition? You take a fraction, and you decompose, we call these partial fractions, by the way. Right, because these are fractions that are part of this, right? And why does this make sense? Because what's the LCD between these two guys?
N squared
N
plus 7.
plus 3 times n plus 4, right? So if I multiply the first fraction top out by n plus 4, the second fraction by n plus 3, and combine them, I would settle on this. I'll get this. So that's where it comes from. How to actually know that or create that, don't worry about that. That's a skill you'll learn next year. But just know for now that 3 over n squared plus 7 plus 12 is the same thing as 3 over n plus 3 minus 3 over n plus 4. Just know that. Okay, so now what we're gonna do is let's see what happens, right? What does all this become? N equals 1, infinity. I'll do a giant bracket because I feel like it.
Can you split it into like 2 different series?
We will in a moment, but for now, let's just write out, right? So if I plug 1, what do I get? Well, let's do this first. Let's write 3/4 minus 3/5. But you are correct. You would get 320. You are correct. What would the next term be? If I plug in 2 friend. Minus 3 out of 6. Okay. All right. What's the next term going to be? Are you seeing a pattern? Okay. Plus dot dot dot. Okay. So what if I plug in if you think about it, you're eventually gonna end off. It's a little bit confusing, but what if you do what if we do this? I'll explain why I'm writing this in a moment. Okay. So what's happening here? You are correct. That's 3/20, right? If you're going to compute this, I think that would be 3/30. Is that right? Or 1/10? If you computed this, I think that would be 3 out of 40 to 1/14, right? So we have 3/20, which is 0.15. We have 1/10, which is 0.1. Yeah, 1/14, which I don't know what that is. It's like 0.0 whatever 7 or something like that, right? So each partial sum, right? Well, actually, it's not partial sums, but each term is getting smaller, of course. I'm not going to calculate the partial sums because it gets a little bit messy. But in general, what do you think? If we come up with the form for S sub n, if I were to add these up, you see a bunch of cancellation happening. What happens to this -3/5? Was it cancelled? What happens to -3/6? And then what I do over here in a general sense, this has to be the last term, clearly, right? Right.
Not just the original thing.
Well, right. Whatever I'm settling on n, right? Like whatever, like the n's a hundreds, right? This would be 103 and 104, right?
Yeah.
What comes before 103 and 104? 102 and 103. What comes before 102 and 103? 101 and 102. So ultimately, by the time we get to the last term,
Just
all these other cancellations happen. This cancel with this. This cancel with this.
Oh, yeah.
That's why it's called a telescoping series, because what does a telescope do? It collapses in the middle, right? You can extend it, but ultimately when you collapse it, what are you stuck with at the ends?
the first
The lens. The lens is right, exactly. That's what you're stuck with. So those cancel, right? What are you stuck with?
3 or 4.
Minus 3 over n plus 4. Now let's take the limit of that. That's what you're really taking the limit of. So what I've done is I found a way to express the partial sum as a formula. like this. So actually, just for the heck of it, what's the first partial sum again? You guys did 3/20, right? What was the second partial sum? Would it be 3/20 plus 1/10, right? Yeah, go ahead. No, because that's where we're ending. Well, it depends on what I choose for. Well, no, yes, it does go on forever. But what if I let n equal 100, right? What if I didn't put infinity up here? What if I made that 100? Then where's that then at 104?
Yeah.
So n whatever this expression is. That's the expression where we're at. And all the other terms will just go away except for the first and last term. But let's calculate the second partial sum, because then we get 1/10 for the second term, right? Second term is 1/10, right? Yeah. Okay. So if I were to add that up, that'd be 4/20 or 1/5. So the first partial sum, obviously 3/4 minus 3/5 is that. If I plug in 2, what's 3/4 minus 3/6? Well, if I think about it, sorry, say again. Wait, then maybe 6 more, 4/20. Hold on.
Not if you plug in n for 2.
Oh, sorry, n for 2, right. I should get
It should be
That's 2 should be 5.
S of 2.
It should be 1/4.
Oh wait, what was this again? This was hold on. That was wait, calculate this wrong. That was 15/30. Wait, 3/30 is 1/10. Wait, I thought it's in wrong here. Hold on a sec. This should converge to hold on. If I plug in 2, if I plug in 1, that's that. If I plug in 2, that's 3/4 minus 1/2 or 0.25. What the name is? Oh, guys, I can't do math. I can't do I need to go back to 4th grade. My apologies. What's 3/20 plus 1/20? 5/20, because I should have made that 2/20. Yeah, okay. I'm silly. No one else tripping. All right. I'm no longer tripping anymore. All right. I was like going crazy. Like I thought I did this right. Okay, 1/4. There we go. My apologies. Yes, we do get 0.25. So this formula will represent the partial sum. Now what I want to do is I want to take the limit of that partial sum formula as n approaches infinity. So let me erase all this junk here. It will, yes, they all do. They all do. Exactly, but when I added the fractions, when I did 3/20 plus 1/10, I actually did 3/20 plus 1/20. I should have done 3/20 plus 2/20. I forgot to change the denominator of the 1/10. That was my fault. So now what I want is I want to take the limit from the term right before that. Everything's getting canceled all in the middle. It's only the ends that are kept.
Right.
The end is n plus 4. No, n plus 4. Okay, let me go back. Okay, let's go back. It's okay. It's okay. Okay, so this, so you're talking about this n plus 1?
Yeah.
From the dot. Because before that was 3/n plus minus 3/n plus 1.
Oh, that's all the same thing?
Yes, this is just continuing. There's just a bunch of stuff in the middle that I didn't write.
N is.
Okay,
I get it.
so for each pair,
So n is.
for each pair, the second number cancels with the first pair of the term right
N
after
is
it.
infinity.
Right, but
Okay, I get it.
but ultimately it has to end there.
Yes.
Okay. So we're taking the limit as n approaches infinity of that expression. Now what happens here, if I take the limit of 3/4, what's that going to be? If I take the limit of the other fraction, what do I get? So it settles on what? Good. So this actually does settle to 3/4. So this will converge. Now, very important. We're not taking the limit of this expression. That expression, if I don't have the E, sigma notation, right? What's the limit of this expression? Yeah. 0. We know that. That's horizontal asymptote. We know that already. But I'm taking the limit of a series. That's the difference. Of the series is this formula. I'm taking a look at this guy, which is 3/4. Hence the sum converges because it settles on a number. So that's what we're trying to, we got to look at through that lens of a series, not of a sequence. Okay, the sequence is determined by that fraction, but we add up all these fractions. We saw when we wrote it all out, oh, it's just 3/4 minus 3/n plus 4. That's what the partial sum is being represented by. I want the limit of that partial sum. That's what I'm trying to do. I'm trying to be careful with my words. I don't mix up sequence and series because that will confuse you guys even further. Okay, so just some things to summarize, right? So infinite series, again, it's a series that goes on forever. You're adding a bunch of terms. The whole converge divergent thing, well, we have to recognize that, A, if you have a sequence, represent the partial sum of the sequence, if that sequence converges and the limit equals some real number, then we can say the infinite series is convergent, right? And we could write it as some sort of number. And that's called the sum of the series. So the sum of the series, what we just said right now is 3/4, right? Or the other one was 3/2 for the infinite geometric series. Otherwise, it's divergent. So this is actually the key idea for this whole lesson today. Everything in this thing falls through. That's the key idea. You have an infinite series, a series moves on part of series, we're adding a bunch of terms. If that sum, we're looking to see that sum converges, and the way we do that, we express as a limits. We do limits and approaches infinity. In the purple box, it talks about there's all these different tests you could do. As I said, there's 10 different tests. We'll just talk about geometric series as a test. The other 9 tests you do next year in AP Calculus BC. So if you look at geometric series, we know AR squared, AR cubed, and so forth, right? That can be expressed as a geometric series from similar notation like this. You know this already. By the way, that's not a geometric series. You know, it looks like it could be. That's because consecutive terms are not a common ratio. That is, the consecutive terms always settles on 1/2 the common ratio. Remember, R's got to be between -1 and 1. We could use an absolute value to consolidate that. So this right here is no different than saying this. No different. It's the same exact thing. If it's greater, of course, it diverges. But let's see what happens when R does equal 1 or -1. So if R equals 1, then what do we got ourselves? Let me clear the screen here. If R equals 1, then you're writing this. N equals 1 infinity. 1 raised to n minus 1 power. So isn't this just a bunch of ones?
A1, whatever. A1 times.
Right, but A1's still 1 anyway. So what are my partial sums here? What's my first partial sum? What's my second partial sum? Third. Does it ever end? No, it goes up forever, right? It's pretty clear that's going to diverge. In general, S sub n just equals n, right? What's my sixth partial sum? 6. What's my 1,456 partial sum? 1456. So it always equals n. If I take the limit of n approaches infinity of this formula, what will be the limit of n? There you go. So it diverges. Right. Because if I take the limit of this, that's just infinity. So yeah, so that diverges. I mean, I know we know this, it makes sense, but this is just looking at through a lens of calculus. That's what we're trying to do here. And then for R equals -1, we'll switch colors for a bit of contrast. We kind of saw this already. So that's -1 raised to n minus 1 power. So the first term is going to be 1, and then -1, then 1, and -1, dot, dot, dot. So this oscillates, right? Well, oscillates. So this also diverges. So yeah, you can't include -1 and 1 for this test of convergence for an infinite geometric series. And that's why we know that the sum would just settle on that, A1 over 1 minus R, because the other part, the 1 minus R to the n, just goes away, right? That just went away. The other part of the geometric series formula, yet A1 times parentheses 1 minus R raised to n power, that just goes away. So, okay. Here we're at the home stretch here. Okay, so determine whether each of these following infinite geometric series converges or diverges. I mean, I think it's pretty obvious. What's your R value here? And because the absolute value of 3/5 is less than 1, this converges. And what does it converge to? Correct. Good. Because it converges, you have to tell me the sum. I want to know it. That's 5/2. By the way, the other series tests you guys use in AP Calcs BC are pretty ridiculous and could be challenging. This is the easiest one, the easiest one. But you'll make sense of it. Ms. York does a great job of teaching it. So, but the other tests you'll do are the ways of recognizing convergence. It's a comfortable one. The other ones are not as comfortable. Yeah. There's things called ratio tests, root tests, things with factorials, all this like crazy stuff you learn. I haven't answered that question for you yet. I'll can we, I'll have some time tomorrow. I'll let you know on Monday morning. How about that? First thing Monday morning, I'll tell you why. Anyway, this one here. What's happening with this one? You can rewrite it like this. Actually, switch colors for a bit of contrast. K equals 1. Yes, but let's re-express the base of the powers. So that's the same thing as 4 to the k, right? Because it's like 2 squared raised to the k power. And this one we could rewrite like this. 3. Let me think about this one here. But it's 3 1 minus. Oh, wait. What? Well, it doesn't make. I'm looking at my notes here and it doesn't make.
It's negative k plus.
Yeah, I'm just. Oh, yes. Here we go. Correct. Thank you. Yeah. What? I don't know anymore. No. Here's what's happening. I do know. I know what's going on. Sometimes. Okay, let's back up a little bit here. Let's do some exponent power 101. You would agree with this?
Yeah.
So you agree with this? We're okay with that? Okay. Here, 3 to the 1 minus k. That's the same thing as saying 3 to -1 parentheses k minus 1. Would you agree with that? I found another one from 1 minus k. Then it goes on the bottom with negative exponent. Sneaky, right? Even I was tripping out. You got that now? That makes sense? So now let's bring it back. 4 to the k, 3 to the k minus 1. Okay. A-okay? No pun intended? Okay, that's not really a pun. All right. Anyway, okay. I'll stop saying case. All right, let's keep going here. K equals 1, infinity. And also you could look like this too. Can I break this down even more? Look at that. Decomposing that to 2 more powers. What's 3 to -1 power?
1/3.
and it flips.
So you bring forward.
Oh, yeah. Yeah, I know. So you really got to be very fluent with your exponents.
We have to write the thing.
Not really. I'm just trying to be as detail oriented so you guys see what's going on. Okay. And right, 4 to the k over 3 to the k is 4/3 raised to the k. Now, is this a geometric series? You bet. I've now rewrote this. It wasn't very obvious in the beginning that was a geometric series. That was really crazy. But by getting crafty and creative with my exponents, right? I can see I can settle on this. What's A1 here?
3.
Well, actually, technically it's 4. If you play 1, but you get the idea. And what was my common ratio?
4/3.
4/3. That's geometric. So R is 4/3. Correct. Right. That's the test you have to do. That's a geometric series test. Comparing aspect R to 1. If aspect R is less than 1, converges. Aspect R is greater than 1, forget about it. Equals 1, also forget about it. Diverges. And this is the work you'd have to show. So what you're doing is you're actually doing a little bit of AP Calculus BC. Ms. York actually teaches you guys usually around February. She does about 2 months or 3 months ago for her AP Calculus BC class. So you're getting a little taste of that right now. You won't see it again for another 7-8 months. And then we'll learn a bunch of other rules and tests down the road. All right, so that's it for today.